Swayam Prabha. Digital India. Educated India.
There are two basic laws of wetting. The Laplace law or the Laplace pressure jump, which tells us the difference between the pressures across an interface when there is surface tension and curvature. And the other law is the Young's law. The Young's law relates the contact angle at the wall to the three interfacial energies that are present in a problem when we are in a partial wetting regime. Now, what we want to do in this lecture is to come up with a general consistent approach to derive both these laws in one go, and we will do this using the principle of energy minimization that we have seen in some of the previous lectures. The analysis will be similar to what we had done for the case of a static meniscus, where in the case of a static meniscus, the goal was to determine the shape of the meniscus. But the goal here is not to determine the shape of the meniscus, but to just derive an equation for the shape of the droplet. Not the meniscus, the shape of the droplet. Right? And in the process, we will basically derive the equations for fundamental equations of capillarity. That is the Young's law and the Laplace law in one go. So the idea is the following. We have a droplet and we want to minimize its total energy with the constraint that the volume is held fixed. Now, unlike in the previous lecture where we knew the shape of the droplet, because we had said that in the absence of gravity, we have a spherical cap, and therefore we were able to do an energy minimization a lot easily. Here we will not assume any shape of the droplet, but instead we will define the shape in terms of a height function, where height is basically the height function is the height of the droplet at any given location from the horizontal surface. And then we will write down a general energy functional, and then we will use a variation approach to derive the Young-Laplace equation and the Young's equation. So let us proceed by looking at a schematic view of the droplet. I have a three-dimensional view of the droplet on the surface, and a two-dimensional view of the same thing can also be shown here. Of course, these figures are not to scale. Now, we have an angle here at the wall. Let's call it as theta E. Further, we will choose a coordinate system in such a way that Z is pointing upwards. My Z coordinate is pointing upwards. And at any given location, the height of the droplet is given by the expression Z is equal to h of x comma y, where h is the height of the droplet at that particular xy location. Now, let's first write down the surface energy of the sessile drop for the finite contact angle. The surface energy of a sessile drop with finite contact angle, we've already seen this in the previous lecture. We'll call it as E surface. This is the functional of energy functional, which further depends on the area. So we have two area quantities that we have to deal with. The area of the liquid vapor interface times the surface energy density gamma or surface tension gamma plus solid liquid times the difference in the surface energy, surface tensions or surface energy densities, right? Now, how do we proceed further? Now we have written down this expression. We can now the idea is that once we have this equation, we can write down the variational derivative, and we set the variational derivative to 0. But before we do this, we have to write this expression in integral form. Written in integral form, we simply get E surface of A becomes dALB, where it's the elemental area element of the liquid vapor interface plus solid liquid minus gamma SV. So this is a solid, sorry. This is a solid times area element along the solid vapor interface, right? So solid liquid interface. So the idea is the following. For the first integral dALV, what we are doing is we are taking a small area element along the surface. Now on this, for this area element, this has an outward normal vector. That's the outward normal vector on the surface of the droplet. And similarly, we have the surface of the solid. That's the contact line that I'm showing. On the surface of the solid, I can also consider another area element. I'll show it in yellow. So I have an area element which is in the XY plane. So the idea is that this at the bottom, this is my XY plane, and Z is the height of the droplet at any XY coordinates, right? So if I take a small elemental area in the XY plane, I could say this is dx and this is dy. And I could also consider, in the case of volume, we will basically take a small elemental volume inside the droplet. This elemental volume is needed when we take gravity into account. So I haven't used this yet, but it will become clear where we write this down. So we have this volume element, we have the elemental areas. Okay, so this is basically the expression for the surface energy. Okay, now we seek the minimum of this functional for a fixed volume. Let's call that fixed volume V of the drop. Okay, so how do we do this? We achieve this by defining an auxiliary function. For those students who may not be familiar with the auxiliary function, please look at the lecture on method of Lagrange multipliers, which is what I'm going to use now. So we'll call the auxiliary function as J, which is a function of A. This is E surface of A minus lambda V, right? So now what is this J? J is also the Gibbs free energy. Functional of the system. This is the Gibbs free energy function of the system. Now we want to include gravity as well. Include gravity, the energy density. Energy density is nothing but energy per unit per unit volume, energy per unit volume of the gravitational energy. What is it? It is just rho g z. That's the energy density. Why is this the energy density? At any given position, if I take a small volume element dv on this left panel that you can see, the total potential energy of that system would be mgh, where m is basically density times dv, that is the mass or mass, times g times the height z. I forgot to mention that for me gravity is pointing downwards. Okay, so this is a sessile drop, not a pendant drop. This is a sessile drop. When we invert the sign of g, it becomes a case of a pendant drop. A pendant drop is a drop which is hanging from a surface, or it could be hanging from a needle. That's a pendant drop. So now that we have this energy density, we'll call this energy density as we have this energy density, so let's first write down the functional. Now the functional with gravity essentially becomes E surface of A plus Eg of A minus lambda V. Okay. Now what is this Eg of A? This Eg of A is a volume integral. It is rho g z dv, right? And what about this volume integral that we have here? This total volume is nothing but integral of dv, right? So we can now combine them, the last two terms, to write down the expression for the surface energies would be like this: gamma times dA liquid vapor interface, that is the surface of the droplet exposed to the air above, plus an integral over the solid surface where the drop is covering the wetted area, that is dA solid liquid interface, plus I can combine the last two terms, rho gz minus lambda of dv. Right. So one of the goals of this this lecture, or one of the goals of this discussion, is to also determine what is this Lagrange multiplier lambda. Does it actually have a physical meaning? We will find out that there is an exact physical meaning, and when you see the final result, you will see that it's a rather intuitive result that we've got. Well, we'll determine the value of lambda, but you can already make a guess. If you look at the last expression, I have rho gz minus lambda. So the unit of lambda should be the same unit as rho gz, and if you work out the units of rho gz, it will be pressure. So lambda will be like a pressure. It at least has the units of pressure. Okay, so we'll find out what exactly it is when we take this analysis forward. Okay, so what are the couple of things that we have to now work out? We have to work out what are these elemental areas. For example, the elemental area, the first one, the easier one, this is along the solid liquid surface. This is just dx times dy, right? So this dASL is simply dx dy. Okay. The elemental area, this is on the curved interface of the droplet, and so therefore we can write down this expression, this area, to be dA liquid vapor is the dA liquid vapor magnitude. Okay, This is a vector, remember, an elemental area vector. Now why is it a vector? Because if you write down a small curved elemental area that is shown on the surface, then there is an outward normal, and the direction of the outward normal gives me the direction of that elemental area, and that's clearly changing as we basically go along the curved surface. Now how do we do this? If you basically write down this expression dA, this is liquid vapor surface, will just be a cross product of these two vectors. Now each of those vectors further can be written like this. These are coming from the normal vectors. So here Hx is nothing but del H by del x, and Hy is del H by del y, and therefore I can now write down the area of this quantity as a cross product, that is I j k dx 0 hx dx 0 dy hy dy, and this is nothing but, I'll do the simplification, I have minus hx dx dy dx times hy dy, the final one is dx dy. So we can now simplify this to say that the area element in the vector form is simply dx dy is common minus hx I cap minus hy j cap plus k cap. I cap, j cap, k cap are unit vectors along I hat along x, y, z directions respectively. Okay. So now that we have got this, we now have a simple way to calculate the area. The area will simply be the magnitude of this quantity, which is just dx dy times 1 plus hx square plus hy square. Okay. We will also require the normal later on. We'll write down the expression for the normal. It's just dA liquid vapor divided by magnitude of this quantity, which is just minus hx I hat minus hy j hat plus k hat divided by square root of 1 plus hx square plus hy square, right? So now we have some of these quantities, and let's look at the last quantity. Okay, the last quantity is dv, and dv is nothing but dx dy dz, right? So this is the last one is an integral over the volume. The first one is an integral over the liquid vapor interface. The second one is an integral over the solid liquid interface, and finally we have a volume integral. Now what we want to do is we want to convert this volume integral into an area integral. How do we do this? We can straight away look at the last one. Last term in the energy functional. Let me write down that term. what is it? We have integral over the volume rho gz minus lambda dv. This is nothing but integral over x, y, z, separate integrals, rho gz minus lambda dx, dy, dz. Right? So this can simply be written as integral over the solid liquid interface times integral over z. Z goes from 0 to h, which is a function of x and y, rho gz minus lambda dx dy times dz. I can simply do the integral over z and I'll simply get area of the solid liquid interface times rho g h square over 2 minus lambda times h dx dy. Okay, this is what I have. I simply now have the expression for the volume integral. I can substitute into this energy functional. Now let's substitute into this full energy functional. Let's label this. Let's call this as equation 1. Okay. The energy functional now becomes final form of the energy functional now becomes J of A becomes integral of gamma times A liquid vapor interface. That liquid vapor interface is now square root of 1 plus hx square plus hy square. Right? This is a double integral because it's over the we'll come to that, but it's an area integral plus that's the first one. Then we have gamma solid liquid minus gamma solid times dx dy, right? Again area integral, and finally we have an area integral over the solid liquid interface. Note that in some cases I write double integral, in some cases I write single integral. These are, I'm doing this, I'm not doing this rigorously, but it's understood that whenever I'm writing dx dy, it's an area integral. So now I want to emphasize that this area integral, first one, all the area integrals are over the ds dy. So they are basically over the solid liquid interface. So in other words, I can simply write this energy functional. If you notice all the expressions here, it's a function of three variables. The height h, its partial derivative with respect to x, its partial derivative with respect to y. This quantity is a double integral dx dy over gamma times 1 plus hx square plus hy square plus gamma solid liquid minus gamma solid plus half rho g h square minus lambda h. This is my final expression that we have got for the energy functional. We'll label this, we'll call this as equation 2. Okay. Now, we can proceed further with this analysis, or we can make a simplification. Couple of things to determine. One is what is the physical meaning of lambda. That's the first goal. To derive the Young's law and the Young-Laplace equation. Okay, and we will see that this is automatically connected to the expression of the Laplace pressure jump as well, or the Laplace law. Okay. Now, what we will do further before we take it up in the next lecture is we will do some simplification here to keep the analysis simple and reduce notational effort, just the effort to write it down, but the analysis is straightforward. We will restrict ourselves to 2D. Analysis to a two-dimensional problem. Okay. So in 2D, the interface depends only on the spatial coordinate hx. Interface height h depends only on one spatial coordinate. So in other words, this height h is simply hx. Okay, and hy is 0. Okay, there is no variation in the y direction, and therefore in 2D case, the energy functional that we have above just simply reduces to j, which is now a function of 2 variables rather than 3 variables. Essentially, I have an integral dx gamma 1 plus hx square plus solid liquid minus solid plus half rho g h square minus lambda. This is what I have, right? Now, what is this integral going from? Let's consider a situation as follows. Let's consider a solid plate which is flat, absolutely flat, and I have a droplet here. This droplet is, let's say, going from some location A to a location B. Okay, that's the x variation along this droplet. So in other words, this integral is going from A to B. Okay, and what we want to now do is to define this function in the quantity in this integrand. This itself is a function of height h and hx. So now we simply have, in a shorter compact notation, we have the energy functional is simply A to B dx of f h hx, right? So let's quickly summarize what we have seen so far. We wrote down the expressions for the energy of a droplet. These energies include the surface energy of the droplet surface, the surface energy of the wetted area. We have also taken the gravitational potential energy into account. And further, we want to do a constraint minimization problem where the constraint is that the volume of the droplet is fixed. So therefore, we have a constrained minimization problem, and we have an energy functional, which is nothing but the total energies that are involved, the surface energy and the gravitational potential energy. And then we have the constraint when we impose this constraint using a Lagrange multiplier. Then what we did was to write down the expressions for these energies in the form of integrals over the height of the droplet. And having done this, we got an expression for the energy functional, which further depends on 3 functions. That is the height, the partial derivative of height with respect to x, the partial derivative of height with respect to y. This entire energy functional, we can continue the analysis directly, but instead, just to keep the analysis simple and reduce the amount of effort that I need to write down these elaborate expressions, I have considered a 2D case, though the analysis is will straight away carry forward to a three-dimensional system. So we have now the expression for the energy functional in 2 dimensions. Now what we want to do now is to consider variations of this energy functional, right? And this variation of energy functional, why would there be a variation? This variation will come about because by looking at variations of this height of the droplet, if the height of the droplet is varied from the height that we want, let's say the height is, let's say, h naught, we want to vary it from that and then find out what is the variation in the energy as well because of the variations in the height. And then we want to minimize this variation, right? So when we want to minimize this, therefore we set the variations to 0. And then using this kind of an analysis, we will derive the Young-Laplace equation. This is something that we had done in the case of a static meniscus, but in the case of static meniscus, our goal was to determine the shape, okay, or get an equation for the shape. We are also doing the same thing here for the case of a droplet. Okay, I'll see you around in the next lecture. Thank you.